All right, my friends, welcome to part 3 of section 9.7, our final installment here. Also a comment, I know that the notes for some of the sections are definitely heftier than the problem sets. I had a hard time finding practice that I really wanted you to do in the textbook, so I tried to build things into the notes that I really couldn't find much of in the textbook, so that's why it's like that. So we really only have, one main family left and then a kind of a side note. And really what you're going to see here is a combination of kind of knowing what type of shape to expect going in just by looking at the form of the equation. And then we're going to go back to t-tables with this family. This family, I know the print is kind of small here. I'll move it down so maybe it's a little bigger. This is called the limacon family. We're going to start with the summary. So limacons have equations of the form R equals A, so some constant, plus or minus another constant times either sine of theta or cosine theta. There are 4 main types of limacons that you'll want to be prepared for. And then what we're going to do in this summary, and you're welcome to pause the video and kind of catch up since I had this all pre-printed. But what we're going to do here is talk about the shapes of the limacons, and then and kind of just briefly talk about why the shapes are the way they are. And then we'll look at an example and have you try to figure out which type of limacon each one is. Oh, and before we go on, if you had B sine theta or B cosine theta, those would totally have been circles, or you could even think of circles as rose curves with just one big fat petal. And I hope it makes sense. It's the adding of an arbitrary constant that makes it so that you wouldn't have just a circle. Okay, the limacon called the cardioid, aka heart shape, has a point at the pole. Let me try to draw this. And then the bottom of the heart is not like your typical, kind of cuspy type look at the bottom. It's very rounded. But that is what a cardioid would look like, where it has a point that comes into the pole, and then it has a rounded opposite side there. Okay, and then a dimpled limacon, or a bean shape, is something that almost would have been a cardioid, but instead of coming to a point where the equation pulls the graph into the pole, it's kind of just rounded at the top here. So it kind of just has, instead of this cusp here at the top of the cardioid, the dimpled limacon or bean shape looks almost exactly like the bottom looks almost exactly like the cardioid. It's just the top. The equation is such that it doesn't quite get pulled into the pole. Okay, a limacon with an inner loop looks a lot like a cardioid. It has an extra little inner loop here. So maybe like this, something like that. Again, it's very rounded at the bottom. And then a convex limacon, at a glance, it looks almost exactly like a circle. It's very, very much related to a bean shape. So a convex limacon at the top, instead of being concave or kind of caving in toward the pole, it is kind of popped out or convex. But maybe something like that, and then it would be very rounded at the bottom. Almost like a toenail or something, There you go. Okay. So just a couple comments. Notice that the cardioid has a smallest R value, or an R value of least magnitude at 0. A dimpled limacon would come from an equation where you cannot get a 0 R value. you either have all positive or all negative R values that would create this shape. A limason with an inner loop comes from an equation that would have a combination of positive R values and negative R values. One of the loops, like maybe the inner loop, would come from negative R values, and the other loop, maybe the outer loop, would come from positive R values. And then a convex limason, very similar to the dimpled limason. And the textbook has more information than what I'm going to share, but for these two, I would just kind of know it's one or the other, and then I would T-table it out, and when I connect the dots, I'd just kind of know which one it is. So there you go. Okay. And so we will be doing a T-table approach, but kind of a strategic T-table approach, so you don't have to work too hard. Okay? Sound like a plan? Okay. All right. So I don't know if this is for sure example 8. I can't remember what example we left off on in the last video. Feel free to number it as appropriate. But the directions are just a graph, and then for part A, you have r equals 2 minus 2 sine theta. For part B, you have 3 minus 2 cosine theta, and for part C, you have negative 2 plus 3 sine theta. So what I'd like for you to do for a second is just try to figure out, just looking at the equation and thinking about how high and low sine can go, try to figure out what kind of limason this is going to end up being. And then what I'm going to do is show you my way of thinking it out. And I'm hoping that when I explain this, that it'll kind of be saying what maybe you were thinking in your head. So sine of theta cannot go any lower than -1, and it can't go any lower than +1. And then if you multiply it by -2, then you'd have a 2 here, and you'd have a -2 sine theta here, and then you'd have a -2 here. And remember, multiplying inequalities reverses the direction of the inequality, so you'd have something like 2 greater than or equal to -2 sine of theta, which is greater than or equal to -2. And I'm going to reverse that. I'm going to mirror image that. There we go. And then the last thing you could do to build up this expression would be to add 2 to all 3 parts. So I'm just gonna do. Okay, and then watch what we're gonna get. We're gonna get 0 is less than or equal to the rule that you were given, which is less than or equal to 4. So what does that mean? It means, so the rule is equal to your R value. It means your R value never gets bigger than 4 and never gets smaller than 0, but it does attain the value of 0. So if you think about that, you're looking for a cardioid that does attain a value of 0, but doesn't have any negative R values. And so if you look at the options, I'm hoping that you're going toward the cardioid there. And this is just kind of a way to think out which one you've got, okay? So once you know which kind you've got, you're expecting a cardioid, the next thing that I would recommend, it would be a T-table approach. And then we'll talk about how to not have to do the whole unit circle. And you're always, if you get bored on your test, you have so much extra time that you want to do the whole unit circle, you knock yourself out. So what I'm going to do is plug in. You're going to see me plug in the 4 corners, because those are always pretty easy. But then we're going to need at least one value in each quadrant just to kind of know how to connect the dots. And so I'm thinking about the sine function, and of everything in the in the first quadrant, what's really easy to plug into the sine function and get something that's kind of clean. And I claim that all the over 6's are relatively easy to plug into the sine function. So you're going to see me plug in 0, pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2, running out of room, and you're going to see me plug in 11 pi over 6, like so, okay? So let's go for it. Plugging 0 in, sine of 0 is 0 times negative 2, still 0, add 2, you have 2. Plot the point facing 0 radians, you're going to go toward it, 2. Plugging pi over 6 in, sine of pi over 6 is 1/2 times negative 2 is negative 1. Add it to 2, you get 1. So we're going to go toward pi over 6 1 unit. All right, plugging in pi over 2, sine of pi over 2 is 1. Multiply it by negative 2, you have negative 2. Add 2, you have 0. So at pi over 2, you're getting 0. And you could put that dashed line that I've shown in the past to indicate that that's where your graph got kind of like sucked into 0. Since you just put a point on the pole, and sometimes you can forget what angle caused that to happen. Plug 5 pi over 6 in, sine of 5 pi over 6, still 1/2. Multiply it by negative 2, you have negative 1, add it to 2, you have 1. So facing 5 pi over 6, we have 1. Wait, did I screw that up? Yes, I did. Oops. 1. There we go. Okay. Putting pi in, sine of pi is 0, so you'll end up with 2 in the end. Okay. 7 pi over 6, sine of 7 pi over 6, that's negative 1/2, multiply it by negative 2, you have 1, add 2, you have 3. Facing 7 pi over 6, you go toward it, 1, 2, 3. Woo! 1, 2, 3. Boy, oh boy, I'm like really missing here. Sorry, guys. Let's put in 3 pi over 2, sine of 3 pi over 2 is negative 1 times negative 2 is 2, add 2, you have 4. So we're going to go 1, 2, 3, 4 toward 3 pi over 2. Plugging in 11 pi over 6, you're going to get the same thing that you got when you plugged in 7 pi over 6. So you're going to get 3, 1, 2, 3. Okay, so we have some dots to connect. You want to make sure that you connect the dots in an order where as theta increased, how did the dots happen? So you went from 0 to pi over 6 to pi over 2. Make sure when you fill this in, it's really tempting to draw just kind of like a cute little heart with a point at the bottom. But if we had done the detail over here that we didn't do, I'm going to turn the paper here so I can do a curve that makes sense. Then we would have found that it actually kind of swings pretty wide. Like so, okay? And so what I'm trying to demonstrate here is just T-table it, you know, but you're also going in with some inside knowledge as to what shape to expect, okay? And so you want to make sure you memorize your forms before you go into the test so you can know what type of shape to expect and then what type of approach that you'd use. And we usually just use T-table approaches, but just kind of a minimal T-table approach depending on what you're graphing. Okay. Let's see about part B here. And this part that I show on paper, you could always show that on paper, but really you could probably do most of the thinking in your head that I'm doing here. But I'll just kind of be conservative here. So for part B, we're thinking, okay, we've got cosine of theta, first of all, is bounded between negative 1 and 1. And then let's multiply that by negative 2. So you'd end up with switching the inequalities. Remember about that. Okay, I'm going to reverse the direction here. I'd have negative 2 is less than or equal to negative 2 cosine theta, which in turn is less than or equal to 2. Now I'm going to add 3 to all three pieces. So I'd have 1 is less than or equal to 3 minus 2 cosine theta, which is less than or equal to 5. And then this is your R value. So we know that we're looking for a limacon where your R values only get as low as 1 and only get as high as 5. So you can rule out the cardioid because cardioids have to be pulled into the pole, and that would be an R value of 0, so you could rule this one out. You could also rule out the limacon with inner loop because one of the loops is always created by negative R values, the other one with positive, and you only have positive R values here. So it's going to be either the dimpled limacon or the convex limacon. And then it would just be, now that you kind of know what shape to expect, you'll go to a T-table. Like so. Excuse me. All right, let's talk about good angle measures to plug into this one. You're always going to plug in the 4 corners because those are easy. And then for a cosine graph, think about in the first quadrant what angle measure is easy and clean to take the cosine of. I really like the over 3s for cosine. because you don't have any square roots. I mean, not like square roots are the end of the world, but it's nice to have some clean numbers, okay? So we're going to plug in 0 pi over 3 pi over 2, 2 pi over 3, pi, 4 pi over 3, 3 pi over 2, and 5 pi over 3, like so, okay? So let's go ahead and plug those in. So plugging 0 in for theta, cosine of theta is 1, times -2 is -2, plus 3 is 1. So you're facing 0, you go toward at 1. Putting pi over 3 in, cosine of pi over 3 is 1/2, times -2 is -1, plus 3 is 2. So you're facing pi over 3, you're going to go toward it 2. Putting pi over 2 in, cosine of pi over 2 is 0. So you're just going to end up with 3 for that. 1, 2, 3. 2 pi over 3, cosine of 2 pi over 3 is -1/2, times -2 is +1, add 3, you have 4. So you're going toward 2 pi over 3, 1, 2, 3, 4. All right, plugging pi in, cosine of pi is -1, multiply it by -2, you have 2, add 3, you have 5. So you're going to go toward pi 5. Yeah, 1, 2, 3, 4, 5. Yeah, there we go. Okay, putting 4 pi over 3 in, cosine of 4 pi over 3, -1/2 times -2 is 1, add 3, you have 4. So 4 pi over 3, 1, 2, 3, 4, and you should see some symmetry here. Oh, wrong graph, haha. You weren't going to see symmetry if I miss. So there we go, go for it. Okay, 3 pi over 2, cosine of 3 pi over 2 is 0, so you're just going to get 3 for this one. And putting 5 pi over 3 in is going to be the same thing as putting pi over 3, so you're going to get 2. So you go toward 5 pi over 3, 2. Okay, and so, whoop, did I do that wrong? Yes, I did. Okay, 2, just 2. Okay, so if you look at this, you know, you can look at the fact that this part, so there's some symmetry here. It's just along the polar axis here. So if you look at it, how would you connect it? Well, I can tell you for sure, you know, this is the wide part at the bottom here. Oops, let's swing it a little wider. You should never look pointing at the bottom. Always make them nice and roundy. Nobody should ever poke their eye out with a limacon. Okay, and so, unless your eye is like right here, I guess. Okay, but anyway, but why would you put your eye there? Anyway, so if you look at the top, you know, what type do you think it is when I connect these 3 dots? Do you think it's the dimpled one, or do you think it's the convex limacon? And to me, it looks like it's the dimpled one, just because of the locations of the dots. And so, again, you are welcome to look in the textbook for more information about relationships between your A and B values that could help you diagnose a little more thoroughly. But I'm a big fan of minimalistic memorization and then t-tabling things out, because you've known how to t-table things forever, and hopefully you know the unit circle. So otherwise this is rough. All right, part C, let's diagnose this sucker, and this again is stuff that you can think about in your head. So here's what I'm thinking. Sine is trapped between -1 and 1. We're going to multiply everything by 3. I'm just building up that middle expression there. Now I'm going to subtract 2 from all 3 parts. Just trying to build this expression here. So now I've got -5 is less than or equal to -2 plus 3 sine theta, which in turn is less than 1. And then this is how R is defined in part C. So you know that your R values are between +1 and -5. So which type of limacon would that be, since R is going to take on some positive values and some negative R values? That's right, it's the limacon with the inner loop. So, and again, especially with this one, it's very nice knowing going in what to expect. So, okay. Same thing as before, look at what trig function's being used, it's sine. And then think about in each quadrant what angle is the most fun to take the sine of. And it's totally up to you as to your idea of fun. But for sine, I really like the over 6s. So I'm going to do all 4 corners and then the over 6s. This is just a matter of having things not take very much time, okay? So you're going to see me plug in 0, pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, let's see, 3 pi over 2, 11 pi over 6, and then that should do it. Okay, now stick tight with me. There's some thinking that we're going to need to think through and probably add a little detail in that may not have already been here. Okay, so let's plug 0 in. Sine of 0 is 0, multiply by 3, add -2, so you've got -2. So you're facing 0, but you have to go away from it too. So there you go. Put pi over 6 in. Sine of pi over 6 is 1/2 times 3 is 1.5. You're adding -2, so you have -1/2. So you're facing pi over 6, and you're going to go away from it 1/2. Okay. Pi over 2. Sine of pi over 2 is 1 times 3 is 3 plus -2 is 1. Okay. Now listen to this. Okay. Okay. So we're going to do pi over 2, 1. Okay. You are going to see me add a point. Okay. And here's my thinking. Your function, which is a continuous function, just went from between plugging in pi over 6 and pi over 2. And my friends, there's lots of angles that we did not choose to plug in just now between those two. And somehow you got a negative R value, and now you have a positive R value. Here's my claim. Your graph at some point between pi over 6 and pi over 2 would have had an R value of 0. Because how on earth could you get from a negative to a positive without passing through 0 if you have a continuous function? So you're going to see me add 0 in. Okay, see that? I just added 0 in because somewhere between pi over 6 and pi over 2, there was a place where you would have added 0. So I'm just going to say there is there's some angle between pi over 6 and pi over 2 with an R value equaling 0 in there, okay? And also, before we have too many points, it's pretty important that you start connecting things. So I got this point first, then this one would have happened, and then this one. So I'm going to connect it. I know I'm expecting a limacon with an inner loop. And you don't want to have too many points go on the page with these before you start connecting them. Okay? All right, let's keep going. 5 pi over 6. Sine of 5 pi over 6 is 1/2 times 3 is 1.5 plus -2 is -1/2. All right, so you're facing 5 pi over 6, but you're going to go away from it 1/2. And then we're just going to continue that loop there. Okay? Putting pi in, sine of pi is 0, so you'll end up with -2. So you're facing pi, but you have to go away from it too, and we're just going to keep connecting the dots, okay? All right, putting 7 pi over 6 in, sine of 7 pi over 6 is -1/2 times 3 is -1.5 plus 2 is -3.5. So you're facing 7 pi over 6, but you have to go away from it 3.5. So that's toward pi over 6. 1, 2, 3.5. Okay, I'm going to go ahead. Now that I have this little inner loop part done, I'm going to finish the dots and then I'll connect it when I'm done. Putting 3 pi over 2 in, sine of 3 pi over 2 is -1 times 3, -3 plus -2, -5. Facing 3 pi over 2, going away from it 5, so that's toward pi over 2, 5. 11 pi over 6, sine of 11 pi over 6, -1/2 times 3, -1.5 plus 2, -3.5. And so you're facing 11 pi over 6, but you go away from it 1, 2, 3.5. Okay, so I'm going to go ahead and turn the paper. I'm going to connect these dots. Make sure that you always keep limacons super rounded as you go. They're probably even more rounded than what I'm showing here, to be honest with you. But there you go. All right, my friends, so there's a limacon with an inner loop. And do watch out for every time your graph passes from a negative to a positive or a positive to a negative, make sure and add a point at the pole, because if you go continuously from a negative to a positive or vice versa, you'd pass through zero at some place. All right, my friends, that is limacons in a nutshell. And so we just have one more example, and it's not going to fit the pattern for any of the families that we've got, but it's just a matter. So, and I'm purposely giving it to you without kind of telling you what to expect, just to give you some time to brainstorm on it, you know, a little problem solving for you. Okay, example 9. Let's have you graph r squared equals 9 times sine of 2 theta. And I hope if you look at this, you can see with the r squared, it's definitely not fitting the patterns for any of the families that we've studied. So this would be a good place to pause the video and see what you would do with it, you know? That's what I would recommend. So assuming you've paused the video and done what you can with it, it would be so cool if you totally figured it out. But here's what I'd recommend. I'd recommend square rooting both sides, and then don't forget plus or minus. So little square root, don't forget plus or minus. So because, you know, if you think about it, we really just want to know what's my r value. So you'd have plus or minus. You could factor the 9 out as a 3. But I'm going to leave the sine of 2 theta in there. So that's the first thing I'd recommend. And then from there, I would just have you t-table it out, really. So, and this is something that surprises people, where you get into graphing polar functions and all of a sudden the t-table is back in style, you know. But it is what it is, you know. You could memorize a lot more, but you'll just forget it, I promise you. So why not just use something you've been good at for a long time, okay? So let's play with this thing, okay? So let's plug in 0 for theta. Yeah, we could actually plug in, yeah, we'll just do 0 for starters. So, okay, 2 times 0, 0, sine of 0, 0, square root 0, 0, times 3, 0. So, all right, we got 0, 0 there. Now, since you have to multiply theta by 2, I'm actually going to go ahead and plug in pi over 12 there. We rarely use pi over 12, but I'm just gonna, okay? And at some point, we'll see that we don't have to do so much, but at first, I'm just going to be cautious. So 2 times pi over 12 is pi over 6. Sine of pi over 6 is 1/2. Square root 1/2, so I'm going to write plus or minus 3 times the square root of 1/2, okay? And then we could simplify that to be plus or minus 3 times 1 over square root 2. And then you could leave it like that, but I'm going to write it as plus or minus 3 square root 2 over 2. Okay, and then let's approximate that really quick. So root 2 is about 1.4. You're going to triple that. Is that about 5.2, I think? And then you're going to divide that by 2, so that's about 2.6, I think. So roughly, plus or minus 2.6. So you're going to go toward pi over 12. You're going to go toward it 2.6 and away from it 2.6. So super fun. 1, 2.6. 1, 2.6. All right, good times. Let's plug in pi over 6. All right, 2 times pi over 6, pi over 3. Sine of pi over 3 is, wait, let me think. Sine of pi over 3 is root 3 over 2. So we have plus or minus 3 times the square root of root 3 over 2. Gross. Okay. Well, root 3 is about 1.7, right? And then you're dividing it by 2. So that'll be like 17 over 20. Roughly. And then, so this is a number a little less than 1. Shoot. Okay. Oh, how do you do this? Anyway. Let's see, a little less than 1. So, dude, Plus or minus, I don't know. Shoot, I'm just gonna grab my calculator, hold on. I don't think this is one that I should have done, but whatever. Okay, 17 divided by 20 is, and then we're gonna square root that. Okay, so we have about, this is about 0.92, and then we're gonna multiply it by 3. Okay, so we have about 2.76. We'll just say 2.8. There we go. Okay, so you're facing pi over 6, so you're gonna go toward it 2.8, and then away from it 2.8. Okay, let's plug in pi over 4. Wait, is pi over 4 gonna be any fun? I think pi over 4 is gonna be way more fun than pi over 6. Okay, 2 times pi over 4, pi over 2, terrific. Sine of pi over 2, 1. Square root 1, 1, good, so we get plus or minus 3. All right, so facing pi over 4, you're gonna go toward it 3, and you're gonna go away from it 3. And I hope it makes sense that like that's as big as a value we're gonna get. We're gonna see this thing like kind of come back toward the pole again. So let's see, what would we do next? Pi over 3? Let's see what happens if we do pi over 3. 2 times pi over 3 would be 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2. And we already did this one, so it'd be back to, we could just steal from ourselves here. So we'd have plus or minus 2.8. So boop, boop, boop. Boop, boop. Okay, let's see, if you plug in, let's just do 5 pi over 12 just for fun. Because this is so much fun. All right, so 2 times 5 pi over 12 would be 5 pi over 6. Sine of 5 pi over 6 would be 1/2. So you'd have plus or minus 3 times the square root of 1/2, which is exactly what we had here. So that would be roughly, I guess, plus or minus 2.6. So go toward that 2.6, go away from it 2.6. Okay. So let's see, let's play with pi over 2. And a lot of this T-table stuff, you know, you could do in your head, I'm sure. 2 times pi over 2 is pi. Sine of pi is 0, so you're back at 0. Okay, so I'm just gonna, I'm gonna show these little dashed lines for places where your graph was sucked in to 0. Okay, so your graph, and so if you connect the dots in the order that we got them so far, we would have this. Okay, so, but we haven't done anything in quadrant 2 yet. So, so let's pick, I don't know, what was relatively easy in quadrant 2, I don't know. Let's plug in 3 pi over 4, okay? I think that's relatively easy. And let's see what happens. So 2 times 3 pi over 4 would be 3 pi over 2. Sine of 3 pi over 2 is -1, and so you'd be left with plus or minus 3 times the square root of -1, aka plus or minus 3i. And as a matter of fact, anything that you plug in quadrant 2 would give you an imaginary result, which would be ungraphable on a polar plane, which only has room for real things. And then you'd find that that's true for quadrant 4 as well. And so what you end up with is what's called a lemniscate. Let's see if I can remember or look up how to spell this. Lemniscate. Okay. Yeah, so this is a there we go. All right, so that's a lemniscate, and so you could recognize the form would be where it looks like it could have been a rose curve, but you have it set equal to r squared instead. And it's almost like a lemniscate is the person who really wanted a rose curve with 2 petals, but realized that because of the limitations on the rules for rose curves, you could never have a rose curve with 2 petals, and so so they kind of outsmarted the rose curve and got their 2 petals. So So there you go, my friends. Expect lots of tea tables, strategic, where maybe you don't plug in all the grungy things that I, for example, plugged in here. I may have over grunged that sucker out. But as you go, you'll keep finding new ways to kind of streamline your process. But it is a combination of memorizing the forms, knowing what shape to expect, and then being willing to tea table things out, except with the rose curves, where I do hope that you understood the analysis that I showed you, where you find the tips of each petal. I would expect for you to demonstrate that on the test over this unit. So anyway, I hope everybody's doing great, and I hope this stuff made sense, and if not, I hope you can get in touch with me about it. Let me know what your questions are. Take care, everybody.